In this video, we are going to prove the Hindboral theorem for metric spaces. In the setting of real numbers, the theorem was rather straightforward. A set is compact if and only if it is closed and bounded. We have already proved the same thing for Rn. However, for general metric spaces, closed and bounded sets need not be compact. We have already seen a couple of examples. So the key fact we need in addition is completeness and a notion called total boundedness. So let's first define total boundedness. This is a much stronger requirement than being merely bounded. It says the following: a set S subset of a metric space is said to be totally bounded, if for each epsilon greater than 0 we can cover S by finitely many balls of radius epsilon. Finitely many balls of radius epsilon will cover the set S, and this can be done for each and every epsilon, however small it is, it doesn't matter. So I must give you an example, but instead I'll give you an exercise. Show that any bounded subset of Rn is totally bounded. Okay. Now what we are going to do is prove the Hindboral theorem for metric spaces. After I prove the theorem, I want you to think about non-examples of totally bounded sets, and the hint is we have already seen examples of closed and bounded subsets of metric spaces which are not compact. Use them to construct these non-examples. So let's state the Hindboral theorem and prove it. Heine Borel theorem. Let X be a complete metric space. Let X be a complete metric space. Then a set K subset of X is compact if and only if it is closed and totally bounded. So this is a stronger statement in the sense that, it's not a stronger statement, it is a weaker statement than Hindboral theorem in the sense that the requirements, the hypothesis is stronger. So if you strengthen the hypothesis, the result will in general become weaker. So the strong form of the Hindboral theorem is simply not true for metric spaces. And one more remark, since it should be rather obvious to you, I forgot to mention it. Any totally bounded set is automatically bounded. That should be obvious to you. So let's go with the proof. One direction is rather simple. The other direction requires a bit of delicacy or a delicateness. A bit of delicacy makes no sense. A bit of delicateness. Now, first of all, observe that K is complete. Observe that K is complete simply because it is a closed subset of a complete metric space, and therefore it's complete. Now let Xn be a sequence in K. We are going to show that it has a convergent subsequence and use the fact that compactness and sequentially compactness coincide for metric spaces. Now without loss of generality, which I abbreviate as W log, we may assume that Xn is not equal to Xm if n is not equal to m. That is, just pass to a subsequence such that this is satisfied. If it is not possible to meet this requirement, then the result is already over. The proof is already over. This Xn will definitely have a convergent subsequence. So we are going to take the case where we can find a subsequence of Xn and remove repeating terms. We will get a subsequence. We are just re-indexing it and calling it Xn. This is just for convenience. The proof will become easier. Now, for a fixed K in the natural numbers, finitely many balls of radius k, say b 1k, b 2k, dot dot dot, b mk k cover k, right? We are starting off with a totally bounded set. So given any of radius 1 by k, sorry about that, okay, given any fixed natural number k, we can find finitely many balls b1k, b2k, bmkk that cover k, and each of these balls are of radius 1 by k. Now this mk in general will of course depend on k. You may have to increase the number if you decrease 1 by, if you increase k, 1 by k will decrease, you may have to increase mk. So I'm not claiming that this mk is in any way fixed or anything. Now suppose, again this is just without loss of generality, suppose b11 sorry about that, I skipped a step. So we have this sequence of distinct terms xn, and b11, b21, comma dot dot dot, bm11 cover k, right, from our notation. Since this set xn is infinite, infinitely many points of the set xn is contained in one of the sets b11, b21, dot dot dot, b, let me just check back the notation, bm11, okay. Simply because the set xn is infinite, infinitely many points of the set must be contained in one of these sets. This is just the pigeonhole principle again. This is just pigeonhole. Now without loss of generality, assume infinitely many terms, infinitely many points of xn is in b11. Okay. Now it is trivial to find a subsequence xnk such that xnk is in b11. Okay. Now what you do is let a1 be an element of this subsequence okay. So choose a1 to be any element of this subsequence. Now what you do is now is the tricky point of the proof. What you do is note that b12, b22, dot dot dot, b m22, I hope I got the notation right, yes, b m22 covers k again, right, covers k again. This just means that infinitely many terms of x and k is in b12. Again, it will be there in one of these the infinitely many terms of x and k will either be in b12 or b22 or bm2. I'm just renaming these balls and assuming that it's in b12. There's nothing really deep happening here. Okay. Again, we can find we can find a subsequence of x and k in k, x and k in B12. Okay. Now what you do is choose A2 from this subsequence such that A2 appears to the right of A1 in the original sequence. Fine. Now repeating this process, we get a subsequence of xn, and by our selection procedure, it is immediate that this sequence an that we have chosen is Cauchy. Now by completeness, an must converge. Remember, an was a subsequence of the original sequence. We have shown that it converges, and it must converge to an element in K simply because K is complete. Proving this proves K is sequentially compact. So a bit of work is required for this part. You have to consecutively choose these terms an in such a way that it's a Cauchy sequence. Right. The converse, on the other hand, is quite easy. Converse is easy. Suppose K subset of X is compact. Then it is certainly closed. And total boundedness is easy. You just use the fact that any cover of K with balls of radius epsilon will have a finite subcover, and total boundedness is immediate. So this concludes the proof of the Heine Borel theorem for metric spaces. Again, I urge you to show that, to come up with many examples of non-totally bounded sets. So let me conclude with giving a notion that's very useful. This is called the notion of relatively compact. A set K subset of X is said to be relatively compact if K closure is compact. Okay, and we have an immediate corollary of Heine Borel theorem. It says any totally bounded subset K of a complete metric space is relatively compact. And the proof is rather easy. All corollaries are usually very easy. So fix epsilon greater than 0. By the total boundedness of K, we can find finitely many balls of radius epsilon by 2 that covers K. that covers K. This is just the total boundedness. It is immediate that the balls of radius epsilon with the same centers cover K closure. So this statement might seem a bit cryptic. I don't want to belabor what is essentially an easy point. What I want to say is you have finitely many balls of radius epsilon by 2 that covers K. Just take these balls and delete the divider by 2. Just take the very same balls but double the radius, the same centers. Those will have to cover K closure. That's a rather easy thing to prove. Now the Hein Borel theorem finishes the proof. So K closure will be closed and totally bounded, and therefore will be compact. So this concludes the proof of the Heine Borel theorem. As I have remarked several times, please do come up with several examples of non-totally bounded sets. This is a course on real analysis, and you have just watched the video on the Heine Borel theorem.